In this video, we are going to study region of convergence in Laplace transform. To understand this concept, we must recall few concepts of Laplace transform as well as the Fourier transform. So we know that for a Fourier transform, a signal x of t must be absolutely integrable. If signal is absolutely integrable, then and then we can find out its Fourier transform. This limitation is overcome in case of Laplace transform. So if signal is not absolutely integrable, we can convert such signals from time to frequency domain using Laplace transform. So here these words are very crucial. In case of Laplace transform, signal is not absolutely integrable. In case of Fourier transform, signal is absolutely integrable. But see now how the Laplace transform actually works on a signal. We know that if signal is not absolutely integrable, integration of that particular x of t signal results into infinite value. So we have to avoid it. Now what Laplace does is, if we go through the relationship between Laplace and Fourier, we have come across an equation that for a Laplace transform, we have an equation like x of s equal to integration minus infinity to plus infinity x of t e raised to minus st dt, where this s is equal to sigma plus j omega. Now if we substitute this value in the equation, we get the values as x of t into e raised to minus sigma plus j omega t dt, further integration minus infinity to plus infinity x of t e raised to minus sigma t into e raised to minus j omega t dt. So this is the equation for Laplace transform. Now if we look this equation carefully, here e raised to minus j omega t is nothing but the basis function for Fourier transform, and the remaining part x of t is our original signal of which we need to find out the Laplace. So this equation signifies that if we want to find out Laplace transform, we do find out the Fourier transform of a signal, but that signal x of t is multiplied by a exponential term e raised to minus sigma t. So here this above equation suggests that we are finding out the Fourier transform of x of t into e raised to minus sigma t. Now what is meaning of this equation? See, though we term it as a Laplace transform, internally we are finding the Fourier transform. So if we want to find out Fourier transform, signal should be absolutely integrable. But we know that to find out Laplace transform, we do not have such condition that signal should be absolutely integrable. So here indirectly we are converting a non-absolutely integrable signal into integrable signal by multiplying that signal with the exponential term e raised to minus sigma t. So from the above equation, if we have x of t into e raised to minus sigma t, this term x of t into e raised to minus sigma t, it is absolutely integrable for certain range of sigma values. It means that a non-absolutely integrable signal is converted into a absolutely integrable signal by multiplying that signal with the exponential term e raised to minus sigma t. But remember here, if we multiply it with this exponential term, for entire range of sigma values, this signal is not absolutely integrable. There are again few conditions where this signal becomes absolutely integrable. So those values of sigma where signal becomes absolutely integrable, that particular values are called as region of convergence. I will repeat it again. We are finding Laplace transform in this case. Internally, for a Laplace transform, we do compute Fourier transform. But before computing Fourier transform, we are doing one step. That step is we are multiplying x of t signal, which is non-absolutely integrable, with the exponential term, so that this x of t signal becomes absolutely integrable. But this product is not absolutely integrable for all the values. This signal is only absolutely integrable for certain values of sigma, and these values of sigma for which this product becomes absolutely integrable, that range of sigma is called as region of convergence. So this region of convergence can be shown graphically. It has x and y axis. On x-axis we have sigma values, on y-axis we have the j omega values. So in this way, for the range of sigma, we can plot the RoC. So with this explanation, we can simply define the RoC as RoC is the set of values of sigma. In many cases, instead of representing it with sigma, many times this sigma is represented with the S itself, S domain of Laplace. It is the set of sigma values for which Fourier transform of x of t into e raised to minus sigma t exists. So remember here, sigma is the real part. So whenever we describe RoC in terms of S, generally the RoC is represented as a real part of S or sigma or simply S. It is one and the same. So we can either refer or represent RoC with a real part of S, or simply with sigma, or with S. So whenever we represent RoC with S, remember that we are only signifying the real values and not the imaginary values. Now let us see the properties of RoC. So the first property of RoC says that RoC is a strip parallel to j omega axis in S plane. So this S plane is nothing but a plot of sigma versus j omega. So this is also called as S plane. Next property. So second property states that if this signal is time bounded, then RoC is entire S plane. Third, if signal is causal, that is right sided, then RoC is also right sided, and this can be represented as real part of S. Right sided means it is greater than certain value, let's say A. Fourth, if signal is non-causal, that is signal is left sided, then RoC is also left sided, and it is represented as real part of S. So on the sigma plus j omega axis, we have the values of sigma on the left hand side of that plot. So here it can be represented as real part of S less than E. Next property, if signal is two-sided, so signal lies towards left as well as right side of origin, then RoC is between 2 points. So it can be represented as like, so RoC is between, let's say, A1 real part of S less than A2. So RoC is between 2 points A1 and A2. So these are the prominent properties of RoC. There is one more important property of RoC, that RoC does not contain any pole. So this is all regarding the RoC. So remember, simple definition of RoC, it is set of values of sigma for which the Fourier transform of signal x of t into e raised to minus sigma t exists, or you may call it as converges. And these are the properties of RoC, and RoC is plotted as a graph sigma versus j omega, which is also called as S plane.